Have you ever gone into a grocery store and used one of those machines, that automatically sorts your coins and gives you back cash? Well, the way that those machines work is by classifying your coins based on their physical attributes. Imagine that we wanted to create a method for, say, sorting US coins into pennies, nickels, and dimes and quarters. Is there a measurement we could use to differentiate the coins? Well, one might be their surface area, or maybe even the diameter of the coin. In fact, we could almost shake the coins on a surface that has round holes in it that are slightly smaller than the diameter of a quarter. Well, then the pennies and the nickels and the dimes, they would all fall through to the second surface. Now, on that second surface, there'd be maybe smaller holes, this time slightly smaller than a nickel, but large enough for dimes and pennies to fall through. Now, if we continued this process, we'd end up with a layer of quarters at the top, and then nickels, and then pennies, and then dimes at the bottom. Now, what we've just constructed is called a classification tree. Now, in this case, the method for classifying a pile of coins. And this is actually an example of a decision tree. Now, in general, a decision tree is a graph that uses a branching method to determine all the possible outcomes of a decision. And now the structure of a decision tree is similar to a real tree. In fact, there's a root, there's even branches and leaves, except you sort of want to think of it as an upside down tree, because we start at the top and then we work our way down to the leaves. So what is a tree? Well, statistically speaking, a tree is a graphical representation of a set of rules. So the tree-based methods, what they involve are partitioning the data into a number of smaller regions, and then we're going to use the data from those regions to try to predict our y variable. Now, when we show trees graphically, the rules that are used to partition our predictor space, our x's, well, it looks like a tree. And we refer to that as decision tree methods. All right, here's how it works. Let's suppose we have one predictor variable, x, and one response variable, y. Now you're going to take all of your data and consider all the possible values of all of your predictor variables. So you're just looking at your x variable. And then you're going to select your x variable at, say, x equal to 3. And that might be the point that produces the greatest separation in y. And we're going to call that a split. So imagine here's your x variable and you're sort of searching around and you're going to look, where is the point at which my separation in y is the greatest? All right? So if x is then less than 3, we're going to send all that data to the left. Otherwise, we're going to send that data to the right. Now notice all we do are binary splits at each of our predictor variables. This is an example of recursive partitioning. So recursive partitioning, it allows us to partition our space into subdivisions with smaller, sort of more manageable chunks of the data. And then we're going to fit a model to those simple local chunks of that data. Now, trees are super easy to explain. And they give us rules that are easy to interpret and also pretty easy to implement. And in fact, they're even easier to explain than linear regression. So decision trees, they more closely mirror the human decision-making process. I mean, trees can be displayed graphically, and they're easily interpreted, even by a non-expert. Also, trees don't require the assumption of statistical models and work well even when some of the data values are missing. Your tree doesn't care about that. It's still going to be able to partition your space. Now, if we've got a continuous y, a continuous outcome, we call that a regression tree, while trees that are for categorical outcomes are called classification trees. Now, regression trees is a simple yet really powerful way to predict our response variable y based on partitioning the predictor variable's x. So here's the idea. You want to split the data into partitions and then fit a constant model of our response variable in each of those partitions. Now, regression trees use the sum of squares. And in fact, the way that we're going to split our data is to find the point of separation, the greatest separation between y minus the expected value of y quantity squared. So how do we use the data to construct a tree that gives us useful answers? Well, there's a large amount of work that's already done on this type of problem, and this lecture is going to give you an introductory description. Let's start with some terminology. First, we have parent nodes. Call that A. So these are the nodes that are at the top of our regression tree that are going to split into lower nodes, which we call child nodes. Now notice that our tree here is upside down. Now our child nodes, this is at B and C. This is the result of a binary splitting of a parent node. So two child nodes are going to encompass the entire parent node. Lastly, we're left with the terminal node, or our leaf node. That's D, E, F, and G. So this is the final partition of the data that contains no more splits. And this is where our predicted values are. All right, let's look at an example in R. The data frame car.test.frame has 60 rows and 8 columns, and it gives us data on the makes of cars from the April 1990 issue of Consumer Reports. Now we're going to use two libraries in R, in particular in this lecture, the rpart and tree libraries, because they help us with classification trees and also with regression trees. So we would load those libraries. All right, here's our data set. This is sort of the first 5 rows of our data set. And you see here we have price. This is in US dollars of a standard car model. And that's going to range from $5,800 to a little under $25,000. Secondly, we have the country of origin. So France, Germany, Japan/USA, Korea, Mexico, Sweden, and the USA. So these are the origins for all of the cars that we're considering. We also have a measure of reliability. This is a numeric vector that's coded between 1 and 5. And then mileage gives us our fuel consumption in miles per gallon. Notice here on the summary statistics that ranges from 18 to 37. We also have the type of car, so compact, small, medium, large, sporty, or a van, and also the weight in pounds. All right, now the first model we're going to consider is one that just uses one predictor variable, weight, to model the mileage. So as long as mileage is a numeric variable, then the tree function is going to assume that we want to do a regression tree model. Now here's our output. Notice that the fitted model shows us the partition structure of our tree. Here, the root level, this is where we have no splits, right? This is the origin, shows the total number of observations, which is 60. It also gives us the associated deviance of the response variable, or the sum of squares. So SSY is 1,355. Now this is followed by the mean response variable for that subset of the data. So for the root, the overall mean is 24.58 miles per gallon. Notice subsequent splits refer to these statistics for the associated data subsets, with the final nodes, the leaves, indicated by asterisks. So for example, check out that first split. It's at the indented rows labeled 2 and 3. So row 2 is split according to weight less than 2,567.5. Notice that 15 observations fell in this category, with a sum of squares equal to 186.9 and a mean of 30.9 miles per gallon. And row 3 is split according to weight greater than 2,567.5. Notice 45 observations fell into that category, with a sum of squares of 361.2 and a mean of 22.47. Now the next level split occurs at both 4 and 5 and 6 and 7. Now the summary function that's associated with tree lists the formula along with the associated data sets, the number of terminal nodes or the leaves. It also gives us the residual mean deviance. So this is the mean square, which equals our sum of squares divided by n minus the number of nodes, or 60 minus 6, which is where we get the 54 that you see here. We also have the 5-number summary of our residuals. Now to examine this tree, we're actually going to plot it. So we can use the plot and the text functions in R to plot our tree and also add the text to it. Here's what we get. Notice here we've got 6 terminal nodes that are produced by 5 different splits. The first split partitioned the data into 2 sets, so above and below that weight of 2,567.5. Notice data values that are below that value go to the left, and then the data values that are greater than or equal to that value fall to the right. Now the second and third splits occurred at weights of 2,280 and 3,087.5. The fourth and fifth splits occurred at weights of 2,747.5 and 3,637.5. Notice here now the values that are in the leaves, sort of at the very bottom of our tree. That gives us the average mileage in miles per gallon associated with each of those 6 final data subsets. So the height of each branch is actually proportional to the reduction in the sum of squares once we do that split. Now for classic regression trees, the local model is the average of all the values in the last terminal node. And now the flexibility of a tree, in other words, its ability to help us correctly classify data, depends on how many leaves it has. In fact, one question is, how large should we grow our tree? All right, well, think about it. A large tree is actually going to fragment our data into smaller and smaller samples, right? And what happens is this often leads to a model that overfits the sample data, and it fails if we want to try to predict. On the other hand, if we've got a small tree, we might not be able to capture the important relationships among the variables. All right, so one question is, why did our tree stop at 6 terminal nodes? Well, in R, the tree function actually limits your tree growth by a couple of ways. Either it's going to force each terminal node to contain a certain number of leaves in it, or if we add a node to the model, then our error has to be reduced by a certain amount. Now, there are default values in the tree that determine those stopping rules, and they're associated with having few remaining samples or splits that add information to the model. Now, we use stopping rules to control the tree growing process, how it should be stopped or not. Here's a couple of common ones. First, the node won't be split if the size of the node is less than the user-specified minimum node size. We'll do an example in a second where we set that. Second, we won't split a node if the splits in the node result in a child node whose node size is less than that of a user-specified child node size value. Third, we're not going to split a node if the improvement in that next split is smaller than some minimum specified improvement level. All right, let's see what happens when we change our defaults to a lower threshold. Here's that code in R. Notice that we've set the minimum split equal to 10. Now, this is the minimum number of observations that have to be in a node in order for a split to be attempted. You'll see here our minimum bucket, or min bucket, is equal to 5. Now, that's the minimum number of observations in any terminal leaf node. We also have a complexity parameter called CP. Here we've set it to 0.0001. So any split that doesn't increase the overall R squared by at least CP at each step is not attempted. All right, so now here's our resulting tree. Notice we now have 7 splits, resulting in 8 nodes. Now, we could change those parameters even more to get a bigger tree. But given the tendency for tree models to overfit the data, how are we going to know when we've got a good model? Well, here's how we know. Tree models use cross-validation. Cross-validation is a technique that splits our data into a training set for model fitting and then also a testing set to evaluate how good that fit is. All right, here's how it works. First, the data is randomly divided into a training set and a testing set. Maybe 80% and 20% or 90% and 10%. Secondly, a tree growing algorithm gets applied to the training data only. In fact, we're going to try to grow the largest tree we can, and this is likely going to overfit the data. Then we have to prune our tree. So what we do here is at each pair of leaf nodes with a common parent, we're going to calculate the sum of squares error on the testing data. And then we check to see if the error would be smaller by removing those 2 nodes and making their parents a leaf. We sort of go around snipping the children off. All right, we keep doing this pruning until no more improvement actually happens in the error on our testing data. Now, the red line you see here is a guide for the cutoff value for our complexity parameter. Here you see the optimal choice of a tree is size 5, since this is the first value that falls below the red line. Now let's create a regression tree that predicts car mileage from price, country, reliability, and car type. So just like we would do multiple linear regression, we can do a multiple tree regression. We can fit all our variables to model our mileage. Now we have an optimal number of splits at 4, since our complexity parameter doesn't decrease by at least 0.01 from 4 to 5 splits. So here's the output of our regression tree. First, there's a split by price. Then you see a split by the type of car, then price again, and then type of car once again. All right, so now that you're warmed up, let's look at another example. In fact, one that's slightly more serious. Here we have a set of 146 patients with stage C prostate cancer from a study exploring the prognostic value of a detection technology called flow cytometry. Now, we want to model the PG time. This is the time to progression of the disease or the last follow-up in years. And we want to model it using a regression tree with the other variables in our data set. Now, here are the first couple of rows of our data set. Notice here in the first column, we want to model that PG time, time to progression. But check out a couple of features. So PG stat, this is actually a binary variable, a 0-1 variable that we're going to throw into the model. Here you see a column for age, so most of our samples of men are around 50 and over. Also notice in that column for G2, do you see in row 2 an NA? We've actually got a missing data value that R is going to handle with ease with the tree function. All right, here's our output. So notice after our first split, this is really where the reduction in the variability occurs. And you can see that by the size of the split, right? So the length of the branches indicates the size of the reduction in the variance. And then we see a few smaller splits. So along G2, along age, along the Gleason score, and then finally we get to several little leaves in our tree. And so this would be an effective way to model this prostate data using regression trees. All right, so you might be asking yourself right about now, is it better to actually run a regression tree or a regular regression? Right? What stops us from just doing a regression analysis on our prostate data set? Well, it actually depends on the problem. So if the relationship between the predictors and the response is well approximated by a linear model, then by all means, linear regression will not only be a better model fit, it'll actually outperform regression tree methods that don't exploit this kind of linear relationship. But on the flip side, a regression tree is one of the easiest understood ways to convey a model to a non-statistician. And furthermore, regression trees are among the very few methods that have been developed that are capable of automatically modeling interactions without becoming computationally and statistically infeasible. Now, a classification tree is pretty similar to a regression tree, except now, instead of using a quantitative variable as our response, we're going to use a qualitative response. So for classification trees, we predict that each observation belongs to the most commonly occurring class of training observations in the region to which it belongs. Now, we're often interested not only in the class predictions corresponding to, say, a particular terminal node, but also in the class proportion of observations that fell into the correct region. In other words, how correct is our model? How many times do we get the correct data set into the correct region? So our accuracy. Now, growing a classification tree is also going to use binary splitting. However, classification trees predict the qualitative instead of the quantitative outcome. So in other words, unlike regression trees, which have those numerical predictions, right, the numbers at the bottom in our leaves, a classification tree is going to make a prediction for a discrete categorical variable. Now, the decision-making input variables that are used to split the data, they can be numerical or categorical, but the outcome is always going to be categorical. So in this case, we use the mode of the terminal nodes as the predicted value. Remember, that's just the most common element that's in that terminal node. So for a classification tree, we predict that each observation belongs to the most commonly occurring class of our training observations in a particular region. All right, let's do an example on our favorite data set, the iris data. Remember, this had 3 different species of iris plants. It had the setosa, the versicolor, and the virginica. Now, we're going to use some of those measurements as covariables. In this case, the response variable is categorical. So the resulting tree is, what do you think, classification or regression? Right, classification tree. All right, notice we've got a really nice tree here. It's got 4 splits and 5 nodes. So if petal.width is smaller than 0.8, we label that flower setosa. And if petal.width is greater than 1.75, we classify that flower as virginica. Now, it's the in-between values that we've got to fine-tune. Notice here, of our 5 nodes, our classification tree only misclassifies 5 out of the 150 flowers for a misclassification rate of around 3%. Now, we could actually see those 5 points graphically by looking at a scatter plot of our data along with those binary splits. All right, check this out. Notice that for petal width between 1.35 and 1.75, we incorrectly classify 2 virginica as versicolor, and we incorrectly classify 1 versicolor as virginica. Now, there is some overlap in those values for a couple of the points, which is why you don't see all 5 of them here on the plot. Now, we also predict setosa correctly with probability 1. And for most points, we're highly confident in our classification. So here, check out the iris prediction. So this actually gives you the probability of predicting the flower according to setosa, versicolor, and virginica. Now, the points that are labeled 0 and 1 says, hey, we know where this point goes. And notice at the point labeled 60, we classify with 90% confidence that it belongs to versicolor and 10% confidence that it belongs to virginica. Okay, so in this case, our classification tree is likely going to put that point into versicolor. But look here at line 107. So this is represented by point 107. We're much less confident in our classification. In fact, only 40% confident that it belongs to versicolor and 60% confident that it belongs to virginica. So here's where those misclassifications are going to take place. Now, classification trees and regression trees, these are easily understandable, and they're transparent methods that help us predict or classify new records. However, they aren't without their pitfalls. In fact, they may not perform well when you've got structure in your data that isn't well captured by horizontal or vertical splits. Check out this example here. Notice we've got a plot of onion growth density at 2 different locations. And while you see sort of a separation in the data, notice if you tried to split this data by horizontal and vertical splits, it's not really going to help you classify the data very well. Well, next time, we'll see a technique called polynomial regression that can better classify this type of data. Also, regression trees can be highly unstable. Right? The trees tend to have high variance because a very small change in your data can actually produce a different series of splits. And since trees don't make any assumptions about the data structure, they usually require us to have larger samples. Lastly, there's no way to capture the interactions between the variables. So although you can split along different variables, you can't really see how they interact in your data. Now, for interaction among variables, you know we can always revert back to the ever-handy multiple linear regression. Or we can try a new method, like polynomial regression, or even step functions. We'll learn more about those in our next lecture.